Thomson discovered the electron for us. That's a big deal, to discover the electron. And he did that by finding the charge to mass ratio and noticing that it was a really, really big number, bigger than any other charge to mass ratio ever found. But he wasn't able to find the charge or the mass, just the ratio of the charge to mass, which we said yesterday is better than nothing, but we want beyond that. We want more than that. We want the charge and the mass. So let's talk about another experiment that was performed a few years later by a guy named Robert Milliken, which actually found for us the charge of the electron. It's called the Millikan oil drop experiment. This oil drop experiment is set up such that we have two parallel plates that would be charged. Now we can charge them any way we want, top plate positive, top plate negative, whatever. Let's make our battery like this. That would make the top plate positive and the bottom plate negative. But again, we talk about variations of stuff. Okay, we could easily see it the other way around. Now what we do is inject tiny little droplets, like microscopic droplets of oil into the gap between these two parallel plates. We get these microscopic droplets of oil by a process we call atomizing it. It's basically like a perfume dispenser. When you take perfume or cologne and you spray it, these tiny little droplets that you can't even see come out, right? We atomize the perfume. Well, we atomize the oil in a similar way. And sometimes that oil becomes, those little tiny little oil droplets become charged. Sometimes they don't become charged, and we have to irradiate this whole thing with X-rays in order to make them charged. But the bottom line is they become charged. Somehow these little oil droplets become charged. Some of these oil droplets may be positively charged. Some of these oil droplets may be negatively charged. Doesn't matter. Some positive, some negative. Now, in the absence of these parallel plates, these oil droplets will all fall downwards because of gravity. Now, these are really small droplets, but there's still a force of gravity acting on them. So there will be, even with the plates, there will be a force of gravity acting down on both of these particles. But with these plates, there will also be an electric force acting. An electric force on the first one acting downward, away from the positive toward the negative. An electric force on the second one acting upwards. I want to focus on the second charge for a second, the negative charge. Now keep in mind, if the plates were reversed, the directions of these electric forces would be reversed, right? So the negative particle would experience an electric force downward, and the positive would experience an electric force upwards. I want to analyze the second particle, this negative particle. There can be essentially four things that can happen to the second particle. One, if the electric force is bigger than the gravity force, it can accelerate upwards. If gravity is bigger, it would accelerate downwards. If the forces are equal, then it will travel at a constant velocity, or it will be suspended. What I want to do first is focus on the negative particle when these forces are balanced. In other words, when it's either traveling at a constant velocity or it's suspended. When that's the case, we're going to say Fe equals Fg. The electric force equals the gravitational force. Don't get that mixed up with the velocity selection chamber of the cathode tube, where Fe equals Fm. The upward electric force will be equal to the downward gravity. Now the electric force is Q times E. The gravitational force is M times G. This allows Milliken, or us, to measure the charge. Not the charge of an electron, but rather the charge of what? We're talking about oil drops here, right? Charge of an oil drop. He hasn't done anything with the electron yet. But here's the thing. When Milliken performs this experiment, he finds that the charge of the oil drop, the charges of all these different oil drops that he measured the charge of, have a pattern. I'll come back to this page in a second if you need it. He repeats the experiment and finds that one of them maybe is 3.2 times 10 to the minus 19. Another one is, I don't know, 6.4 times 10 to the minus 18. 1.6 times 10 to the minus 18. 9.6 times 10 to the minus 19. 1.6 times 10 to the minus 19. 3.2 times 10 to the minus 17. All these different charges of oil drops. But he finds that, look, they're all multiples of that number. This one is twice that number. This one is, 40 times that number. This one is 10 times that number, and so on and so on and so on. They're all whole number multiples of that one number. And what's the conclusion that he draws from that? Two things. One, there is what we call an elementary charge. The smallest possible charge. The elementary charge is 1.6 times 10 to the minus 19 coulombs, which corresponds to the charge of an electron. Remember, we talked about the elementary charge a little bit back in Unit 1 when we needed the charge of an alpha particle or a proton. Now we're wondering what it is. If I do 500 experiments and they're all multiples of 1.6 times 10 to the minus 19, and 1.6 times 10 to the minus 19 is the smallest number I get, then that must be the elementary charge, the smallest possible charge. The second conclusion he draws is that charge is quantized. Charge is quantized means that it can be a certain number or a multiple of that number. Your energy when you walk upstairs is quantized. Your energy on the first step is 150 joules, let's say. On the second step, it's 300. On the third step, it's 450. On the fourth step, it's 600. You can't have 493. You can have 450 or 600, a multiple of 150. Energy is quantized. Charge is quantized as well. They're all multiples of that one base number, that elementary charge, 1.6 times 10 to the minus 19. Milliken has just discovered, not the electron, that had already been discovered, but he's just discovered the charge of the electron. And now you can imagine if Thomson had found the charge to mass ratio to be 1.76 times 10 to the 11, and Milliken finds the charge to be 1.60 times 10 to the minus 19, then their results combined can give us the mass, right? All we'd have to do is calculate that using Thomson and Milliken's results combined. Okay, let's have a look at this question on 15.3 on page 763. It says an oil drop with this mass is suspended. Okay, we know that if this question said that it was traveling at a constant speed, we'd analyze it the same way, because when it's suspended or traveling at a constant speed, we set Fe equal to Fg, not Fe equal to Fm. That would be the velocity selection chamber, Fe equal to Fg. How many electrons has the oil drop gained or lost? That's a little bit tricky, but we'll see here. QE equals m times g. We're going to solve for Q here. It's mg over E. The mass is 8.2 times 10 to the minus 15 times 9.81. The electric field is 1.0 times 10 to the 5. I get 8.0 times 10 to the negative 19. All right, this doesn't answer my question. How many electrons has been gained or lost? How many? A number. You want to find a number of something, what do? Total by the single, right? Total by the amount of one. So we're going to divide that by the charge of one electron, and we get 5 electrons right there. Gained or lost, though? Gained or lost? Pay really close attention to what I'm about to do. Just stop writing. Pay attention to this, okay? We have an electron, negatively charged. It says the electric field is downward. If the electric field is downward and the gravitational force is downward, The electric force must be, sorry, we don't know that that's a negative particle, right? We just know that it's a particle that has 5 excess or 5 fewer electrons. But we do know the electric field is downward. We also know the force of gravity is downward on it, and we know in order to balance that, the electric force has to be upward. Positive or negative particle. If the electric force is up in a downward electric field, what kind of particle is it? Yep, negative particle, right? Okay, the force is opposite to the direction of the field for a negative particle. Therefore, it would be 5 electrons gained in this case, making it a negative particle. Whenever you get a question like this, draw out that picture. They'll give you the direction of the electric field. Okay, if it's suspended, we know the electric force has to be upward to oppose gravity. If the electric field was upward, it would be positive. If it's downward, it's negative. Positive, it loses electrons. Negative, it gains electrons. A couple questions for homework on page 763. Let's deal with questions 1 and 2. B, don't ignore the gaining or losing 3 electrons. Don't ignore the direction of the electric field. Okay, and again, a reminder, mathematically, these are pretty straightforward. Okay, this part of the problem, the gaining or losing, the upward or downward field, that's what gives people trouble. Draw the picture with the field direction and the force direction, and it should be a little bit easier for you.